on with lesson 3.5, and we're proving that this function is tends towards all real numbers as defined by f of x equal to 1 over x squared is uniformly continuous. All right, so we want to recall that a function with domain S, function with domain S is said to be uniformly continuous. It's said to be uniformly continuous if for all epsilon greater than 0 there exists a delta greater than 0 such that for all x and z, we use x and z again, are elements within our domain S with the absolute value of f of x minus f of z is less than epsilon whenever x minus z, the absolute value of the difference of x minus z is less than delta. Okay, so the problem with this is that in our proof, here's the difference. In our proof, we want to prove that f of x is equal to 1 over 1 plus x squared is uniformly continuous. So we want to let epsilon be greater than 0. We want to choose a delta, but we don't know what that delta is yet. So we're going to have to figure that out through using scratch work again. So we're going to set the framework of our proof, and then we're going to go ahead and figure out what delta is, and then go back and write our formal proof. Then for all x and z, that's element in domain S, for f of x minus f of z is less than epsilon whenever x minus z, the absolute value of x minus z is less than delta. But first we've got to figure out the scratch work for that. Okay, so we start with our framework of our f of x minus f of z is less than epsilon, and since f of x is 1 over x squared, this will be 1 over 1 plus x squared minus f of z, so that will be 1 over 1 plus z squared, and we're saying that's all less than epsilon. So from here we need to get a common denominator, so that means we have to multiply, use purple. Since this is 1 plus z squared, we need to multiply 1 plus z squared over 1 plus z squared times 1 over 1 plus x squared, and put this in parentheses, minus 1 over 1 plus z squared, and we need common denominator 1 plus x squared, so we got to multiply that by 1 plus x squared over 1 plus x squared, because we're trying to combine these two terms together. Okay, so from there, that's going to equal 1 plus z squared, close it, minus 1 plus x squared in parentheses. And that's all under one common denominator, 1 plus z squared times 1 plus x squared. Okay, so we distribute that negative, and that'll be 1 plus z squared minus 1 minus x squared all over 1 plus z squared times 1 plus x squared. Okay, and so the ones are going to cancel out. So the ones cancel, right? And they go to 0. And so we get z squared minus x squared all over 1 plus z squared times 1 plus x squared. Okay, so from here we can factor that. Z minus x, z plus x, and that's all over 1 plus z squared, 1 plus x squared. Okay, so we can, since this is z minus x, absolute, so we can split this right here. And off to the side here, since the absolute value of z minus x is equivalent to the absolute value of x minus z, because it's absolute value, you know, even if it comes out negative, then the absolute value is going to make it positive. So we're looking at just the number of units, basically the difference, the absolute value of the difference. So z minus x, absolute value of z minus x is the same as absolute value of x minus z. Okay, so we can say that x, since z plus x is the same as x plus z, we'll make this x plus z over 1 plus z squared times 1 plus x squared, close that, times, so we're splitting, since it's multiplication, we can just split that, and that'll be x minus, absolute value of x minus z. Okay, so from here we can use what we call the triangle inequality to show them that they're bounded by some number. Well, how does the triangle inequality work? Triangle inequality. Well, if you have a vector here, we'll call that the magnitude of x. And we have another vector here, we'll call that, and that's the magnitude of y. Then the sum of those are the magnitude of x plus y. But x plus y is, because of the triangle, this side is going to be less than the sum of the other two sides. So therefore, x plus y, the absolute value, the magnitude or the absolute value of x plus y is going to be less than magnitude of x plus the magnitude of y. So that's why we can split this, okay, and we can say that this is less than the magnitude of x over 1 plus x squared 1 plus z squared, and plus, trying to squeeze this in here, the absolute value of z over absolute value 1 plus x squared times 1 plus z squared, and that's all that is multiplied by the magnitude of x minus z. Okay, so from here we can say we can make this smaller. Now we need to make this smaller than some number. One thing we can do is to drop the z squareds on the left and drop the x squareds on the right. So rewriting this, I'm just going to rewrite this down here so this is the same as this. Absolute value of x over absolute value 1 plus x squared, and I can split this times 1 plus z squared plus absolute value of z over 1 plus magnitude 1 plus x squared, absolute value of 1 plus x squared times 1 plus z squared. Okay, and then here we have x minus z, the absolute value of x minus z to the side. Okay, so from here, let's look at this for a minute. We know that if the absolute value of x over the absolute value of x equals 1, then the absolute value of x over 1 plus x squared is going to be less than 1. Well, the larger the denominator, the smaller the number. So 1/3 is a larger denominator than 1/2, but it's less than 1/2, right? So the larger the denominator, the smaller the number. So we can say that, so we can drop, what we want to do is we want to have just the x's. So if we drop the z squared, we're saying that this fraction, this expression, is less than if we dropped. So this is less than the absolute value of x over 1 plus x squared. And so we can say the same thing for the z's. Z over z is going to be larger than z over 1 plus z squared. So this will be plus the absolute value of z over 1 plus z squared. And all of that is multiplied times x minus z. Okay, so we're saying that since x over 1 plus x squared is less than 1, then we can say that this is less than 1. So this expression is less than 1 plus this is less than 1. So if x over 1 plus x squared is less than 1, then z over 1 plus z squared, that's less than 1. Excuse me. So that's all going to be multiplied times x minus z. Okay, so from there, 1 plus 1, that's going to be 2 times x minus z, the absolute value of x minus z. And so, since we said early on that x minus z is less than delta, then we can say that this expression is less than 2 times delta. And since this expression is less than epsilon, then we can say that if we were to divide 2 to both sides, we can identify delta as equaling epsilon over 2. Because that's all, this whole thing, right, is less than epsilon. So now we can identify delta as epsilon over 2. Now we can go ahead and go back and write our proof, and we can identify delta as epsilon over 2. We can say f delta is equal to epsilon over 2. So let's go ahead and write our proof. So from here, we can say that, now we can write our formal proof. Mix this up. Formal proof. We can say let epsilon be greater than 0. We choose a delta is equal to epsilon over 2. So that's what we're looking for over here. Then for all x and z are elements of interval S, or domain S rather, then f of the absolute value of f of x minus f of z is less than epsilon whenever absolute value of x minus z is less than delta. So we put in for f of x minus z of x, f of z rather, 1 over 1 plus x squared minus 1 over 1 plus z squared, and is less than epsilon. So now we go through this whole process again. So we already know that this is going to be 1 plus z squared minus 1 plus x squared. So this will be, because we're combining those two, this will be 1 plus z squared minus 1 plus x squared all over 1 plus x squared 1 plus z squared. And so from there, we're going to go ahead and simplify that. And so that's going to be, that comes out to be 1 plus z squared minus 1 minus x squared over 1 plus x squared 1 plus z squared, and that becomes z squared minus x squared over 1 plus x squared 1 plus z squared. Close that. That's a square there, square, that's a z. Okay, so from there, since, so we can factor, right? Z minus x and z plus x, 1 plus x squared, 1 plus z squared. And so from there, we can break this off. Z plus x over 1 plus x squared 1 plus z squared times x minus z. And we've already established that z minus x is the same as x minus z. And so from the triangle inequality, we can say that this is less than the absolute value of z over 1 plus x squared times 1 plus z squared plus the absolute value of x over 1 plus x squared times the absolute value of 1 plus z squared, and all of that is multiplied times the absolute value of x minus z. And since z over z equals 1, then the absolute value of z over z 1 plus z squared is less than 1 because the denominator is larger. So therefore we can drop the z squared, the x squared on the left, drop x squared on the left, and drop, since this is an x, we want to drop the z squared on the right. So that will, this is less than z over 1 plus z squared plus, and that's absolute value of x over 1 plus, and here we're dropping the z squared because this is smaller than this, 1 plus z squared. So you can keep going smaller because as long as it's less than epsilon, then we're fine. And all of that is multiplied times x minus z. And so since z over 1 plus z squared is less than 1, we can say that this is less than 1 plus 1, and then x, absolute value of x minus z, we said that that was less than delta. So we can make that delta. So that's less than 2 delta. And since delta equals 2 epsilon over 2, we can substitute epsilon over 2 in for that. So that's 2 times epsilon over 2. The 2's cancel. And so therefore, what we have is epsilon. So what's that saying? What's all this saying? All this is saying is that f of x minus f of z is less than epsilon, and we've proven it. Okay, because if this is true, then on our interval, right, this is x and this is z. This is f of x minus f of z, right? That no matter where that x, wherever this is your delta here, wherever your difference in x and z are, they're going to be the same. That's going to be the same as the difference for f of x minus z of x. And so we've proven that with this all turning out to be epsilon. And there we go, we've proven it. And that is the end of this video.